Should we bust this guy back out? Come on. Hold on. Yo, Mr. Austin! My dude! Hey dude, how's it going? Alright, we got the TTS on. Let's hear it, yo. How's it going, everybody? Welcome into the stream. Come on, feel that. Feel those jabs. Woo! I'll be getting a drink. I'll be right back, guys. All right. There we go. Costco muff for the boys. How's everybody doing? What's going on? Oh, chat's dead. Ain't nobody here. All right. All right. Let's get into this. All right. So, I wanted to... Hey, what's going on, Charlie? Thanks for the chat, my guy. Yeah, Tim, we're going to make some money. We're going to make some money, Tim. We're going to have to add you to the... You're going to have to become our top finance broker. All right, so I wanted to go over the Black-Scholes model today. So we're working on our better options script. So my idea for this is I want to at least kind of get into not really like bot trading at all. Like that's really not my goal. My goal is kind of more into using, data analysis and Python scripting and the power of a computer to basically compute value of contracts for me in mass, so I don't have to do that, right? So, not that I ever do compute Black-Scholes models by hand, right? We're a degenerate, right? We're not actually a trader. But I think it could be definitely useful to maybe level up our game and give us some edge. If we have the ability to compute a Black-Scholes model across, let's say, 50 tickers for, let's say, their top 5 contracts that are at the money. Right. Yeah, we try here. We try sometimes. So, I mean, so it's, yeah, I want to get more into it. I want to be more disciplined. I want to have more of an edge to my game. I have been winning, but I do have some losers, and I am tired of having those losers. So, but honestly, I might switch to selling. I might switch to selling. The seller wins way more. Let me tell you. I mean, we're still up like 50% year to date. So really good so far still, but I don't want it to be just bull run luck. So let's go ahead and let's get into this. Let's see what we can do here. So let's talk about this. So first off, if you guys aren't familiar with what an option contract is, it's really like not honestly too difficult once you kind of actually understand it. It's kind of honestly a lot like programming. It's kind of hard to wrap your mind around it at first, but then once it sticks, it's like riding a bike. So yes, you are kind of betting on like a future outcome. That's the whole part of an option. With the stock, you own a portion of the company at an asset, but with an option contract, you have the right to own, and that's the key difference. And you need to understand what the difference between owning and the right to own. And your right to own is usually at a specific price within a specific time allotment, right? So, and these two factors are what are some key players into determining your overall value, both intrinsic and extrinsic, of the actual option contract. So, let's go ahead and dive into the Black-Scholes model and what it actually does. Well, I didn't really explain an option contract well. So let's just say, you have a certain price of a stock, and if the stock, exceeds that price, you have a strike price for your option contract. If the stock exceeds that price, on the date of your expiration, you have the right to own those shares at that price, which is lower than the current price. So you have the right to own those shares, so you can exercise and then sell those shares for the difference, or you can let it ride and keep going. right? That's just a very simple breakdown. It is not that simple, but that was just a very quick. So what is the Black-Scholes model then? The Black-Scholes model is one of the most important concepts in modern financial theory, also known as the Black-Scholes-Merton BSM model. It's used to determine the fair value of an option contract. This mathematical equation estimates the theoretical value of derivatives based on other investment instruments. It considers the impact of time and other risk factors in its calculations. It was developed in 1973 and is regarded as one of the best ways to price an option contract. The Black-Scholes model is also known as the Black-Scholes-Merton BSM model. It's a differential equation that's widely used to price option contract. The Black-Scholes model requires 5 input variables: the strike price of an option, the current stock price, the time of an expiration, the risk-free rate, and the volatility. The Black-Scholes model is usually accurate, but makes certain assumptions that can lead to predictions that deviate from real-world results. The standard BSM model is only used to price European options because it doesn't take into account American options could be exercised before the expiration date. Right. So, developed in 1973, the Fisher-Black-Merton, whatever, yeah, Scholes. Black-Scholes was blah, 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 blah. Okay, here we go. It's a stock future contract with a log normal distribution of prices following a random walk with constant drift and volatility. Okay, the Black-Scholes posits that instruments such as stock shares or futures contracts will have log normal distribution of prices following a random walk with constant drift and volatility. The equation uses this assumption and factors in other important variables to derive the price of a European-style call option. The Black-Scholes equation requires 6 variables. It's theoretically possible for option sellers to set rational prices with these variables for the options that they're selling. The model predicts that the price of heavily iterated assets follows a geometric Brownian motion with constant drift and volatility. It incorporates the constant price variation of the stock, the time value of the money, the option strike price, and the time of the option expiry when it's applied to a stock. Black-Scholes assumptions. Right. So these are assumptions that are made, and these are our values here, right? So the call option price is equal to S, the current stock or underlying price, right? Times N, a normal distribution, right? Of D1 and a normal distribution of D2, right? And then D1 is equal to this equation here, and D2 is equal to this equation here. Interesting. Okay, I want to go here and see what it can also tell me.
Bottom says, what's your opinion on Master of Science in Information Security?
No idea, dude. I don't really have an opinion. I'm ignorant in that area. Sorry, man. Anybody here have an opinion? Let me grab a napkin.
Bottom says thanks for trying. says, I think cybersecurity is a great field.
All right. All right. Let's keep going here. Let's talk about the Black-Scholes model and how I
Tim says, Mike, did you see the TAP controversy?
T-app. What exact? I heard that they leaked their female user database, right, and their IDs and stuff. But what is the T-app? Like, is it like for iced tea or like boba tea? I was like, what? I've never heard of this thing before. How did it have so many people on it? Okay, the Black-Scholes model is a classic way to estimate the fair value of a European-style option, especially calls. While it's not perfect, especially for American options, dividends, or volatility shocks, it's a strong starting point for spotting undervalued option contracts. The formula for a call option is, right, and for a put option is this, where it gives me these. Don't show me any.
T, officially known as T Dating Advice, is a mobile phone application that allows women to post personal data about men they are interested in or are currently dating.
A mobile phone application allows women to post personal data about men they're interested in or currently dating? What? Oh, like spill the tea? Oh, come on. Cringe. People do that? Like an anonymous rant about your boyfriend?
Punch says, LOL what?
Like, get a therapist. What? That's crazy. Okay. Let's do this. You guys will see my history here. CS skins. I was looking at CS skins. I want to talk about the Black-Scholes model and go into detail about how we can use it to apply to American options. I typically trade, American blue chip or tech stocks, and I'm not really familiar with European markets. How can we apply the Black-Scholes model and its theory to find options within our options chain that could potentially be undervalued? And what does that actually tell us about the option contract in detail? I want to know more about the Black-Scholes model as it is and how I can use it to my advantage. There we go. This is a prompt right here, boys. This is a prompt. Right, kind of deep, quiet understanding how to practically use the Black-Scholes model in U.S. markets, which trade American options, not Europeans. Gives you an edge traders never explore beyond surface level Greeks or IVs. What's the Black-Scholes model fundamentally is? Okay, gotcha. At its core, the Black-Scholes model is a mathematical formula designed to find the theoretical value of a European-style option. It does this by solving for the expected payoff of an option discounted back to the present under a set of assumptions. No arbitrage, constant volatility, log normal distribution of returns, no dividends, but they're built into the model if known, frictionless markets, and no early exercise. So yes, it's built for different style of contracts, but the model is still very useful as a baseline pricing benchmark in the American market. Even though the most U.S. options are American style, the vast majority of them, especially in liquid large cap stocks like Apple, Microsoft, and Nvidia, are not exercised early in practice, especially if they are out of the money or have significant time to expiry. Thus, the Black-Scholes model is still a reasonable model for estimating the fair value of most calls and puts, comparing against market prices to spot potential mispricings, build scanners and screeners for cheap options. Just keep in mind, deep in the money options, or those near ex-dividend dates, might deviate more from the Black-Scholes values due to their early exercise potential. Black-Scholes model undervaluation does not equal guaranteed edge, but it points to contracts worth a deeper look. What does it mean when the market price is not equal to the Black-Scholes model price? If the market price is lower than the BSM price, then this suggests that the option is undervalued relative to the model's assumptions. So, why might this happen? Liquidity, wide bid spread ask, underestimated future volatility, mispriced during news or uncertainty, short-term inefficiencies. You, the trader, can exploit this by buying options that are priced lower than the model predicted value, selling or avoided options that appear richly priced. But more frequently, you're looking for contracts where the market is not properly accounted for the risk or probability distribution of future stock moves. But more importantly, you're looking for contracts where the market is not properly accounting for the risk or probability distribution of future stock moves. How to spot undervalued options using the Black-Scholes model. Here's the mental model. Here we go, guys. No, I just have the regular. I haven't paid for nothing, Punchy. Yeah, isn't that literally doxing? Hey, do you think we can hit 2,700 today? 2,700, Mr. Tim? Tim's got to pull out the bot accounts. All right, let's keep rolling. How to spot, so understand the inputs. For each contract, identify these inputs. Implied volatility from the options chain. Use the Black-Scholes model to get a fair value. Using those inputs, compute the BSM theoretical value. Compare it to the market price. Look at the last traded price or better. Okay, hold on. Use the Black-Scholes model to get a fair value. Using those inputs, compute the Black-Scholes model theoretical value. Use BSM to get a fair. Using those inputs, compute the BSM theoretical value. Got you. And then step 3, compare the market price. Look at the last traded price or better, the midpoint of the bid-ask spread. If the BSM value is greater than market price, there's a potential undervaluation. So the BSM value is like the fair value of the option, right? In this model's eyes. Investigate further. Is the IV low compared to the stock's historical volatility? Is volume or open interest low? Maybe price is stale. Is a macro or earnings event upcoming? Maybe market is underestimating the move. Are skew/smile dynamics affecting this contract? Is there part of larger market structure mispricing? You calculated the theoretical value of a $2.30 for a call. It's trading at $1.85. That's a 45-cent difference per share, and might signal a good entry opportunity. And mispricing something in the market that you don't, something the market sees that you don't. Stock expected to stay range bound. Use this discrepancy as a signal, not a conclusion. Black-Scholes model is a tool for edge. The real power comes when you use the Black-Scholes model to build relative value map across the option chain. Compare options across strikes and expirations. Spot where time decay isn't priced correctly. Combine Black-Scholes model pricing with interesting. I wonder if we could compute the Black-Scholes model price across, let's say, all the contracts for that week on a Monday, right? And then actually take the price and plot them and see where we have like discrepancies, the large discrepancies between each X point on the graph. Like if we see some larger deviations between the two lines, we could have some potential players too, right? And we could cross-reference that against historical IV, and if it's low enough, make a play. I don't know, guys. This seems like some pretty juicy. We're learning here, guys. This seems like some pretty interesting stuff we got going on here. Mr. Tim. In short, theoretical mispricing for practical edge equals opportunity. I'm thinking, could I take a ticker symbol, let's say Microsoft, or maybe something a little bit cheaper, Robinhood stock. Well, maybe not Robinhood stock because that experiences quite a lot of volatility due to it being kind of a quote-unquote meme now. We would want something more constant with less fluctuation day to day, right? To kind of fit better to this model. So maybe a stock like a mid-cap that still has strong growth potential. Could we compute, let's say on a Monday, the Black-Scholes model for the at-the-money option across all days of the week, and then cross-reference that against the bid-ask spread price average for the actual underlying price of the contract? And then if there's large fluctuations between the two lines on a plot between each X point, we could have a potential player to then look deeper into IV and volume. Structured data information how to use an analytical edge over most retail traders. Let's walk you through the ideal step-by-step sharpen reasoning behind it and then clarify how it fits into a practical trading system. You're proposing to select a stock, preferably mid-cap, low daily fluctuation, decent liquidity. Each Monday, analyze the at-the-money option for the nearest expirations. Compute the Black-Scholes theoretical value for that option each trading day, Monday through Friday. Also track the market price average for the option over those same days. Midpoint of the bid-ask spread or use last trade, plot both over time, theoretical versus market. Identify periods where there's a significant divergence. Flag those moments for deeper inspection. Is it mispricing? Is it IV shifting? Is it liquidity dropping? Yeah, Black-Scholes model value depends on input. The inputs daily, the underlying price days to expiration IV. Meanwhile, the market may react slowly, overcorrect, or underprice, be illiquid, or driven by news. When the Black-Scholes model is and actual price deviates significantly. By tracking this, you're building a quantified deviation signal between what the math options be worth and what the market is actually pricing at. How could you would use this divergence signal when the difference widens? Asked.
Hi man, how's going?
Mohammed, dude, what's going on, Mr. Mohammed man? Did volume dry up? Maybe price is stale and the BSM is ahead of the market action. Is a one-day anomaly or a trend repeat mispricing for a stronger hedge? Or are you really doing? Okay. Let's see what we can do here.
Mohammed says, what you doing, Meg? MAI engineer,
We're just looking at just some trading models. Just trying to have some fun in Python and code up some models. Just to go over some options data that we're pulling from Yahoo Finance here. Nothing too crazy, but kind of fun. I want to see if we can maybe just get a little bit more experience messing around with this kind of stuff. I like to trade sometimes. Well, sometimes, all the time. Okay, so right, this gets the option chain. So the chain.calls and chain.puts. So this gives us Microsoft calls and puts in the form that we wrote this a couple days ago, right? And this is all the call options, and these are all the put options for Microsoft here, right? Now, we would need to find the at the money contract, right? So the at the money contract is when the in the money flag turns from false to true. So this is our at the money contract for Microsoft at the 512 and a half to 515, right? So 515, you're in the money on a put. So on a call, actually, let's look here on a call. So 512.5, you're in the money here on a call, and 515 you're out. So you're above 512.5 but below 515. So let's go ahead and try something out here. So we need a couple of things here for the Black-Scholes model. We need a call price. Okay, so we have a stock here. We have data here. Okay. So let's compute let's write a function here to compute def. Do we want to do the Black-Scholes model of it's a specific option, right? Let's do ESM. We'll call Black-Scholes model. I'll make this a little bigger for you guys. And then let's put in self here, and then let's go ahead and we need to also put in do we need anything else here? Strike price, we can get all that stuff, put option price. So we're gonna need a call option price, right? So we're gonna put in the option. Right. Now what we might want to do is create an actual option, right? Create an actual option and save, like have that be an object too would be also interesting. So, but for like, oh man, there's a lot we could do. I mean, is it kind of overkill? But it could be helpful for the future, right? To have an option, right? Right. Now, if we define an init here, right, the option would take in a few things such as strike price of a float, it would take in an expiration date in the form of a let's go maybe we won't use date time yet. Let's just make it a string for now. And let's go, it would take an expiration date, it would take strike price. Well, it really would take kind of all of these, right? Yeah, so it kind of would take all of these. Right, so let's just take a quick class to extract this information. So it would be contract symbol.
Mohammed says, cheers.
Thanks, Mohammed. Appreciate you coming in and following along, my guy. You're awesome. Thanks so much, my guy. How is being an AI engineer? That's pretty cool. Get paying the big bucks. So let's do symbol. Strike. Okay, let's just do this. Strike price. Expiration. So this would be just strike. Contract symbol. So last trade date. Last trade date.
Mohammed says he definitely.
The last time someone traded it? That could be useful information. I think this is a datetime object. Okay. Last price. Right. Bid, ask. These are floats.
Are you man in Idaho based?
Are you what? Man in Idaho based? I'm in California right now. This will be a float as well. Yeah. Volume, float. Open entry.
Boston resident. Mohammed says, we're looking for digital marketing specialist with great customer service skills.
Nice. Digital marketing specialist. What does that entail? Great customer service. I was the customer service. Are you guys my customers? Muffin. All right, boys. Applied volatility in the money. This is a Boolean.
Tim says Mike won Best Customer Service Award at his prior restaurant job.
My girlfriend she was really good at customer service at the Olive Garden. I work as a formulation chemist for those that are new here. My name is Michael. I'm 26. I have a degree in human biology and a minor in chemistry. Graduated back in 2021, and I've been working since then as a formulation chemist. I'm a scientist too, mid-level. I'm kind of approaching scientist three, pretty much. There's kind of nothing really standing in my way, I don't think, rather than just kind of politics. But yeah, it's all good. I enjoy it. I don't really care. It's whatever. And yeah, and I've been teaching myself how to code for about a year now. Sorry, I just came back from being sick, you guys. You might tell my voice a little bit still. But yeah, I had a couple of days, quite a wild day break because I was just, in the mud, you guys. You guys know that I don't take breaks often. I stream pretty much every single day for the past year. Coding live, reading books, doing projects, courses. But if I was really out of it, if I really wasn't streaming or coding, you guys know that I was really not feeling good. I like to be productive. Okay, anything else we need here? Contract symbol, last trade date, strike. Right. Percent change. So bid, ask, oh, then change. Then percent change, volume, open interest, implied volatility, in the money, contract size, and currency. Perfect. So now what I'll do is, let's go ahead and set these variables, right? Just copy this.
Mohammed says we need digital marketing specialist. Yes, pay rate about $30 per hour on average.
I'll do self dot. Let me just do this real quick. Right, and then I'll say equals to.
Tim says apply mine.
It's in Idaho, you said? Percent change. There's gotta be an easier way. There's gotta be an easier way. Is this really how it is for us Pythoners out here that make classes by hand? This is brutal. Alright. Jeez. Dang. Okay. Now we have at least an option contract that we can quickly build up, right? And then like get reference of, so of like get price and stuff. So let's go like this. So I'm gonna go from classes dot option import option. And then let's go ahead and make this be an option for its type hint. And then let's go ahead and do this. Okay, we're all set up here, I think, to write this model in. So it goes like this. The Black-Scholes price is equal to, for a call, let's do this. Call was true. It's true. Right by default. Yep, equals true. So then I'll say if call so if call, then we're going to do this model. S is the current stock price. So we're going to do self dot data index of, let me look up why finance IPI. No. Info, price history, quarterly income statement. So can I go ticker dot? Let me do this. Let me say print Microsoft dot data dot price history. None. Get price targets, balance sheet, cash flow, earnings. Okay, so is there a average 50-day, 52-week low, market caps, bid ask? Market day low, open, executive team. Price. Current price. Okay, so we'll go dot info. So I'm gonna say def get get current price self, and what we're going to do is we're going to return self dot data dot info of current price. So then I'm going to say print Microsoft dot get current price. I'm going to set this as a property. There we go. Okay, so Microsoft stock closed today at 512.57. So we should get 512.57 here. Boom. Okay. Now there's also a regular market price, it says. Huh, that also works. Now it also says that you could use data dot or self dot history or self dot data, so self dot data dot history. Oh, maybe not. Okay. Noise. Okay, so we'll keep that as a property. All right. Okay, let's go back to this. Oh, let's go here. Let's go. Okay. And then okay, so now let's go back to here. Woo! Almost spilled my drink. That could have been bad. Take a drink here. We got double drink going on. We got double drink. You guys got double drink? I love me a double drink. Okay. So if call. So let's first do this. Current price is equal to. Tim, we're getting scammed. So C is the S sub 0 is the current stock price. Let me do this. S equals self dot get current price. K is equal to the strike price. So this is going to be option dot strike. T is time to expiration in years. For computing T. For computing T from a contract. in years, how would Okay. So the time to expiration. So we're going to do option dot days until expiration. We'll take this property that we have yet to write. We'll write it here in a second. And we will divide this, right, by 365. Right? Do you count the current day? Excellent nuance. This comes up a lot, but yes, you typically include the current day. Okay, so we'll write this. And then let's keep going here. Let's keep on going here. Bring up my little notes here of the Black-Scholes. Where are you? Where are you? Here you are. R is the risk-free interest rate, annualized. Use the U.S. 10-year Treasury yield. According to 4.41% according to recent data. At 4.42%. I'll probably write something to scrape this. But I'll put it in here for right now as a parameter, right? So I'll do R, which is going to be a float, right? You pass in R. And we'll say that R is equal to R, given. And I'll say rate here, just so you can risk-free.
Mohammed says made him not HR manager, hehe.
Okay, so then sigma. How do you do a sigma in Python?
I made AI developer, yes.
So we need to go here and go import numpy. We need to do
Mohammed says, I'm.
No, sigma is a numpy. How can you do the sigma variable in... I think you can do it in Python, can't you?
Mohammed says you can apply at your own pace. Just let you know.
Okay, let's just do this. So, I wonder if I can just, can I take this? I can take this. No, I can't. Sigma. This is just the implied volatility, right? So this is going to be the option dot implied volatility. Okay, so we have these models here. So then let's say D1 is equal to so we have to compute these two. This is what I'm looking at here. So we need to compute these now by inserting these variables into this D1 function and then overall into our call or put function with D1 and D2. So D1, we need to do so this is going to have a log to it, right? Oop. Right, log. So math.log, the s of 0, so s divided by k plus r plus sigma squared divided by 2 times t all over sigma times math dot square root of t. Right, r plus sigma squared divided by 2 times t, right? And then we divide that by sigma math square root. Square root G. Yeah. I think that's right. Now let's compute this D2, which is just D1 less than.
Mohammed says Tim off cows and obviously go to the strip club. What else is Idaho night?
This here. Mohammed tripping. Mohammed wildin'. Mohammed, are you on a completely? This is just completely random. Are you here on visa? And are you in Idaho on visa? Okay. Okay. So if call, right, we're going to compute now our Black-Scholes price, right, which is pretty easy. So this is just going to be theoretical call price, right, is equal to, this is the function I'm looking at right here. So it does say we're going to have to use the norm though. The only place I know where this is, I've seen it once. Is it SciPy? I think so. I think it's SciPy stats. Now let's go source bin. Okay. So the theoretical call price for a call option is S times the norm of D1 minus K times how do you do E? Forgot how to do E. This is norm. CDF, and then you go.
Mohammed says, I'm originally from Australia, Arab based, now based in Idaho. I'm a U.S. permanent resident, green card holder, heh.
By want to import.
Stoic says, "Yo suck, Michael Deming." Stoic says, "How have you been doing?"
That sounded like you suck, Michael Deming, with the TTS. Hey, dude, how's it going, Stoic? Welcome back in, dude. Appreciate you being here. So NumPy. No, it's math. Sorry, not NumPy. It's math.x. Right? Exponent. So it goes, then it's negative r times t
Stoic says, "It's been a while since I have been here."
times norm.cdf
Says, "You grew a long way."
of d2. This is a hard function. I'm like,
Stoic says, "I remember you being at like 600 subs."
nice, dude. Yeah, isn't that cool? Yeah, we've been grinding.
Stoic says, "And now you're at almost 3K."
Oh yeah, we've been grinding, my guy. Appreciate you coming in here. We're almost there. So then D2, right? Else, we're going to return this. Right, else we're going to return for a put option, it's k times math.exp negative r times t times the norm.cdf of negative d2 minus s times norm CDF of d negative d1. All right, that's the Black-Scholes model.
Stoic says, "Are applying for software engineering jobs or no?"
Your boy, we had an interview for a software engineer chemist position that we blew.
Stoic says, "Because you are good at Python."
I know, I think I'm pretty good at Python. They told me I wasn't. Oh, I got really nervous, my guy, and I choked. I just like, dude, I got so nervous.
Stoic says, "I have been learning pandas and NumPy and I am not good at it tall."
Oh, me too, man. So now we need to do this T, right? Total days till expiration for this option, right? So the option, we're going to give it this a self dot days to expiration is equal to compute, or is equal to compute days till expiration. Okay. Now this function right? We're going to take the contract symbol, right, which is this guy here. Which is the 250801.
Mohammed says, have a good night, mate. See you later. I'm gonna retire and rest.
See you, dude. Thanks for coming in, my guy. I appreciate you for joining me. So T
Stoic says, it's okay, try again. Prism says hello. Prism says good MRNG.
Hey, dude, how's it going? Welcome, man. Welcome back. So, we need to compute.
Stoic says it goes like this. I think you might miss 29 times, but on your 30th try you make it.
The options days until expiration. Right, we need to compute this. So the option, when created, strike a last price and then money contracts. But the ticker that made it, right? We're going to generate options from a stock, right? After we generate the option chain, we have calls and puts. We can generate option off those. Now I'm generating off of an expiration index here. So let me also return the expiration date as well, right? So now what I'll do is we'll get the expiration date as well. Right, that was used to generate this option chain, right? From this expiration index. Let's print the expiration date here. There it is. So we generated the options chain for Microsoft. Good. And it overrode these two files and got new data. Nice. That was for today. Cool. And now we're getting the expiration date there. Perfect. So now what I'm going to do is I'm going to apply so these are Y finance vars. These are custom vars.
Master says we're not doing leap code.
Hey, how's it going? We're doing some scripting for some options right now and stuff. Finance stuff, custom vars. So self dot expiration date is equal to the expiration date passed into the constructor as a stir, right? And so what we'll do is when we generate a stock, we generate an options chain and an expiration date for these options chain calls and puts, right? Now we have this days until expiration. So now what I'll do is I'll take the option and the days until expiration. I'm going to take datetime.date.today, right? I think that's what you do with datetime, right? No, I think it's just datetime.today, right? And we'll save this. Right, that'll give us a datetime object for today. And then I'm going to say delta is equal to the absolute value of self.expiration date less than today. So I want to print date. This is a stir. So when you convert this to a date time dot and you convert it to a date time object. You do this by doing datetime.strip string time, the date string, I'm going to put this at So what happens if I just go, hold on, let me do this. Let me print datetime.today. Like this. Okay. If I go to datetime.today.date, a date object. If I return the function, I get just the date part. Now if I subtract from that, what if I just do like a string of 2025-04-12? Datetime stir, right? Okay, so now let me go datetime dot so this is string new datetime parser string like time. So strip time, and you put in self.expiration. Let's just do the new year, right? End of the year. 2 arguments when given. Format equals stir. Oh, so we need the format. So to do the format, you do what, like this dash percent month dash percent day, like such. Datetime dot datetime. Okay, so then if I just do datetime dot datetime, $155 days away. Okay, so it would be this right less than date time dot today, right? So if I take this, I print this. Cool. Okay, 145 days. Now if we just need to change this to be self dot expiration date, right? Now I'll return the delta here. I'll return this, but I'm going to return the date of it. Not onto the print statement, but inside of here, there. Object D. Well, the time delta object, so it would be days. It would just be a property, right? Such 154. Okay, so that will do that. And so then I can just get rid of this. So now in the stock, I get the expiration date. Now I can call so it's going to give me this here. So if I want to build an option, right? If I want to build an option off of this stock, off this option chain that I was given from the calls, let's say, right? So let's go test option is equal to an option where the contract symbol, excuse me, Microsoft calls, which is if you print Microsoft calls, we get just a bunch of rows, right? It's a data frame. So then if I wanted to so if I want to generate an option off of this, I need to take the heading for every row in the data frame and match it to the instance variable in the option. So I'll say call options is equal to a list where we're going to have option contract symbol, right, equals to so say can I print an index of Microsoft calls? Here. So get loc. That's right. What happened? I gotta think back to our pandas. Oh no. Get lock. Okay. Okay, so if we say for, let's say calls is a list here. Let's say for call in Microsoft calls. So for call in Microsoft calls. If I wanted to access dataframe.columns get lock dataframe.index location of 2 so can I do this? So this just prints the first row. Okay, let's do this. Column and row. What is iter rows? So you could say for what's that iter rows? Contract symbol equals to row contract symbol. Right? I think that's what you do. And then you go, what's the next constructor? last trade date. To row last trade date. Strike last price. Bid, ask, change, percent change, volume, open interest, implied volatility in the money, contract size, and currency. And then we would say to be the last price, bid, ask, change, percent change, volume, open interest, implied volatility in the money, contract size, and currency. And an expiration date, which will be given via this. From here. Right, and then what we're going to do is go calls.append so then let me make this a option type equals to call, and we'll put on here an option type, a stir, and we will reference this here. Right, so we give it a call, option type. Okay, so then what we're going to do is we're just going to go option and then I'm going to give this a under stir of option self, or say self dot option type dot title. Put option or call option return. We'll do self dot contract symbol actually. Right. And then I'm going to put, that's fine. So now what I'm going to do is I'm going to print here the calls. Option object. And there we go. There they all are. Okay, so we are appropriately generating all the options for this, right? So we'll say, I'm going to say, after we initialize, I'm going to print self dot option type dot title right? So now if you run, we're going to get a bunch of prints. Call successfully generated, and then we'll get those. Okay, printing at each one. Nice. So now we have each option as an actual option. Oh, it's the index. Okay, so this is the index, and then the row. Okay, and then in iter rows. Access the rows. Okay, so nice. So now we're getting every option, which is good. Let me quickly run to the restroom. Sorry guys, I didn't mean to have the music stop. Okay. So let me take this. This goes here. Let me go import stock. Import option. From stock. Import stock. Option. Import option. This, which is option. Module not found option. Module name option, huh?
Ray says hello, Mike and everyone.
Hey, how's it going, my guy? From dot classes. Huh. How do I do this? I did push it.
Tim says open some cases, Mike.
Cases? There we go. Okay. Okay, so let's figure out why this isn't working. A module named option. From dot classes. No module named option. Why isn't this working? I hate importing. Dot classes dot option import option. So from classes.stock import stock. Classes.option import option. Stock, I'm importing option into stock. Module found. Does it work with this? Module found option. Here's
Rope says, why did you want to start coding?
discharge option. Here from classes option. I think that'll work. There we go. Mount here. Stop. Move this. So now I'm testing. It runs. Okay, so now we're getting all of our options contract, which is good, right? So now we are getting access in our testing.py to be able to make things and do stuff, right? So we can test within a separate file here, outside of the stock class itself. All right, cool. So what's next on our agenda? What do we need to do next is the question. So currently we have the ability to generate all the options contracts for a given expiration date. Okay? We can generate all the option contracts for a given expiration date and save them within an array. Now, we should probably provide a get options chain, like filtration for like a limitation, like, right? Meaning like the first, so in our stock.py, in our get options in our chain here, what we're doing is we are going getting the options, getting the expiration date from the options, generating the chain from that expiration chain, and then exporting it if it's exportable, if you want it to be exported. Now, and then we return the expiration date, the calls, and the puts from the chain. Now, what I could do is I could limit the amount of chain that is generated, right? So I'll say, if I put here a limit, which by default is none, right? Which would be an int, which by default is none, right? You could provide a limit. Now this would generate the chain. Now I would say, now what happens if I print, the chain is a pandas data frame, right? So can you take a slice of a pandas data frame? Okay. So what I need to do is I have a chain here. If I print the chain, I run this. Here's the chain. All right. What's this? Where am I printing? Why is it printing this? Huh. Oh, this is part of the options chain. Oh, got you. So chain is options chain on the expiration date. And then we write the chain here. What is all this junk? What am I printing? If I remove this print chain, I run. Oh, I don't get it. Okay, so that is a part of the chain. I didn't know that. Chain.calls. Oh, okay, so it's all the calls together. So what I want to do then is I want to access the chain. Or what am I wanting to do? Right now I'm taking all the calls and I'm putting them into an array after they're generated objects. I was trying to apply a limit to this options chain to limit these, right? Okay, so if I say the limit is none, that would make, so on the chain here, and then I would go, returning chain.calls, chain put, okay. So the limit, I would need to go through the chain, find the strike that's at the money, and go plus 5 from there, or plus the limit from there. Right? So that generates data frame of chain of calls and puts. A chain of calls and puts, and so in my testing, I'm returning those here, and then I'm iterating over them and generating options. When I could just go into that and generate it. So then let me take this. Right. Let me take this. Go into stock. Go over to chain. Go calls. For every row in chain calls.iter row, we're going to append the option to the call. And then for every option, in the chain puts, we're going to make this a put and do puts equals an array, and we'll do puts dot append option, and then we're going to return calls and puts. Right, so testing, this will now return Microsoft calls and puts as objects. I don't need to do this or this. I should be able to just say now, for every option in Microsoft calls, print option. There they are. Beautiful. So call option and put options were generated, and then there's all my call options. Nice. Cool. So now I'm getting all of my option objects. Right, if I print the type of what option is, right, I get class of option. Right. So now that I have all these options actually out of these data frames, which is nice, I can kind of do my work with them now, is we can, right, we built in the, now what I'll do is I'm going to make this a list comprehension to make this a little bit cleaner. Option for row for row. Just keep it like that, I guess. So then we'll go here, we'll go get add, and we'll commit a message that says add option conversion within okay, so then what we can do is we can compute okay, so where does that take us here? So now we have a list of all the options for Microsoft for this given expiration date, right? Cool. So what I can do now is I can generate. Now an option has a what? Does it have a current price? Last price? Bid, ask, and change. Right, so it does have last price. So we can access the last price and compare that to the Black-Scholes model for every, right? So for every, so we'll say Black-Scholes price is equal to a list, right? We'll say for every option, we're going to compute the option dot on a stock object. So we'll go Microsoft dot Black-Scholes model on the option, and we're going to do the Black-Scholes price dot append. We'll say prices dot append, and then I'm going to do print the Black-Scholes model prices, and then I'm also going to do is I'm going to go current con prices equals to array, and for every option I'm going to go current con prices dot append the option dot last price, right? And then let's print I'm going to print prices, and then I'm going to do this Black-Scholes is equal to this, and current is equal to this. We're going to tuple current and Black-Scholes together, and we're going to do prices dot append this tuple. And then let's go ahead and print prices. Moment of truth. Boom. Oh, we're missing rate. So our Black-Scholes model, we need to provide a rate, which in the current market is 4.42%, or 0.0442%. Days to expiry. Oh. Days until expiration. Days to expiration. Days to expiration. Days to expiration. Now if we run this, option object is an attribute compute days until, do you mean days to expiration? Line 47. On options dot pi. Yep. Days to expiration. All right, here we go. Ready, guys? Here we go. All right, so what we've done here is we have this Microsoft, which is a stock, which basically takes the ticker object from Y Finance, converts the ticker object into a stock object, which is our custom object, right? I'm just kind of refactoring the ticker object into our own custom stock object. Pretty much the same thing, but just slight reformatting for our purposes. And then we're taking that Microsoft stock and we're using a method called get option chain, which returns the option chain with the expiration date, the list of calls, and the list of puts. And this is a list of options objects. And the expiration index, this is like the first expiration, second, third, fourth, fifth in the list of expirations, basically. So the further you get out, the further it expires with this integer value here. And so what I do here is I then get the list of Microsoft call options objects. I get a list of Microsoft put options objects, and I get the expiration date. I then calculate the Black-Scholes price for the option given the current rate, and I calculate the I get the current price of the option, right? And then I append to the prices list a tuple of current and the Black-Scholes so I can compare them side by side. And what I'll do is I'll also append a third tuple value item here for the to identify the strike price of the option. Right? Cool. Let's try this. No. R doesn't have a value. Great. Lots of bugs. Almost there. All right, there we go. Let's see what we got. Okay, so for the 240 strike. Hey, dude. How's it going? Hey, how's it going? All right, so what is this telling us? What is this telling us? So this is telling us for the 240 strike, we have a current price of 272.46 per contract. And we have a Black-Scholes model price of 272.65. So not much difference there. And let's actually also throw in another value here. I'm going to append the it's going to be Black-Scholes minus current divided by current. Okay, so for the 240 strike, and then what we'll do is let's call round to these. And then we'll do a round to 0.2 or 2 digits. Yeah. So then we're going to take this we'll do change is equal to this guy here, right? The change, what would be like a percent change? Yeah, BSM value to every price. And then what we'll do is we will multiply this. We're going to round this to 2 decimal places and multiply this by 100. And then we'll put the change here as a third tuple option. And I'm just going to put this. So all right. Cool. So now what is this telling us? We need to identify, we can identify percent changes -7%, 495. So we're at 512 for the strike price. So we're like here. 507, 510, 512 here. 10.7 for the current contract price and 8.91. It's overpriced. Okay, so let's go ahead and now let's go talk to them. Let's ask GPT for some feedback here. Hey Roxanne, how's it going? Hey Rob. Okay. I think I have written the model and I want some feedback and regarding my data. Don't show me code, but let's talk through my code and what it is doing. So I'm gonna give it, I don't want to give it too much, but I need to give it kind of a lot here. I'm gonna probably basically have to give it all I wrote today, which I don't really like to do, but I want to get some feedback regarding this because I've never done something like this before, or for like stocks really. I want to make sure my Black-Scholes model is right for one, and then so I am using the stock class to generate options for each for a given expiration index. These are then fed into a loop to generate the Black-Scholes and formatted in a readable tuple. All right, here we go. Moment of truth. You're on the right track and your code is structured well for clarity. You create a stock object using yfinance.ticker to give you access to metadata, historical prices, and option chain. You get the options chain, you select an expiration index 0, meaning the closest expiration. You iterate through the calls and puts for the expiry. For each row, each option contract, you instantiate a new option object, parsing all the contract metadata into attributes: strike, bid, ask, IV. These are returned as a list of option objects. If export chain equals true, it saves call and put change as CSV, great for manual inspection. For each option, here only calls, you compute the theoretical fair price via Black-Scholes. You use the current stock price from Yahoo, self.getCurrentPrice. You derive D1 and D2 using norm CDF to return either the call or put price depending on flag. You compare the computed theoretical value of the Black-Scholes against the actual last price from the market current, calculating a percent deviation. You output a strike price, current price, theoretical price, and a difference. This sets up a strong what you're doing well. Clear separation of concerns, thoughtful method, names, and class organizations, use of properties, data serialization options via export chain equals true. You're not hard-coding the expiration date. It adapts based on available chains. You computed days to expiration on each option dynamically. You're normalizing IV. What price used for comparison, you're comparing last price, last trade versus Black-Scholes. This is used for historical mispricing, but mid-price, so mid-price is bid plus ask divided by 2. Okay, so let's do option bid plus option dot ask, right? And then let's divide this by 2, and then let's put a round here. As such. Okay. Okay, change that over. Oh. Right, so that's how it's supposed to go. Option bid plus option. There we go. So based off this information, if we were to look at Microsoft at the 5/12, right? These are pretty negative, meaning that these are pretty overpriced. So I'm going to give it my data set that was generated. Here is the data based on what I see for at the money strikes around 5/12 for Microsoft. These cons are negative percent change for the Black-Scholes to current price, so they could indicate overpriced. Your data shows you ran the Black-Scholes model on a range of Microsoft call options compared. The Black-Scholes theoretical shows the current mid-price average of the bid-ask, interpreting the results. Around the strike prices of 510 to 515, you're seeing that we have an average around negative 17. This indicates the current market price is higher than the theoretical Black-Scholes value by about 16 to 20%. That's a negative delta, and you're correct identifying this means the options are likely overpriced relative to the model. Why this happens, especially at the money. Even though these are options at the money, which should have reasonably accurate BSM pricing, there are a few possible reasons for overpricing. Implied volatility is inflated. Traders might be expecting a near-term move in Microsoft earnings, Fed announcement, etc. Black-Scholes model uses your assumed volatility, but the market price might price in higher IV, which inflates the premium. Is my BSM model not using the current option IV as the factor? Correct. Your Black-Scholes model is not using the option's actual implied volatility unless you're explicitly fetching it from the data source and passing it in. You're passing it in as the rate as a volatility sigma input. That's a historical value or a fixed assumption. No. No, my sigma is the option.iv. Your function does use option.iv, assuming that the option implied value is already set correctly for each option, not none or defaulted. And self.getCurrentPrice is returning a float and not a method reference. See below. So you're intending to use IV and the code supports that, but hidden possible issues. Check that the option applied value is none or too low. If it's none or 0, it's 0.1, you're being. I'm confused. Why is it not understanding? You're technically using the option's implied volatility as your sigma, which is correct in principle, but in practice, the value might not be what you think it is. Here's why. Why finance simply returns implied volatility in decimal form, but scaled improperly. For example, this might mean 41.23%, but that actually might be. So based off of here, based off my export, IV is really small, meaning they are factoring down. You're on the right track, and your Black-Scholes one of these options. But why have a percentage? Implied volatility. Implied volatility of the Microsoft call option. Let me look up the implied volatility on my broker. of Microsoft right for the closest dated 515 call is 60.54% at the close. So the 515 call has an implied volatility of 0.58. Okay, so these are given in decimal form then, it looks like. So then the 240 call is like 0%. So it's like 3. Oh, but it's like all the way just rounded. So then you should get your first implied volatility spike around like 440-ish. To like 90%. Okay, so let's say based off this, IV is in decimal form as the 240 in the money strike would have near 0 IV. Implied volatility, that's 3,359, which is not realistic for deep in the money Microsoft call. For normal large market, which is usually 20 to 40% range. Implied volatility divided by 100. So that would take 3.3 divided by 100 to give me 0.033. So we would just take the implied volatility that would be 50%. Let me look up why finance impl volatility Python. Python over here. Okay. Just wrote the whole thing for us just now. Cool. So then what would the implied volatility be coming from? So if the sigma is greater than 1, I'm confused. So the implied volatility 78. I don't really get it. I don't really get it. Why is it different? Applied voltage should be filled directly, but that's a critical error. The value is 3.33, which represents a 333% implied IV. If the sigma is greater than 1, divide the sigma by 100. But what if it's less than 1? What is Biochemist doing? The option implied volatility comes as a decimal. This means 0.33 means 33% implied volatility. Finance already divides by 100 internally when scraping or parsing from Yahoo's API. So if you're using the value of an option object populated by Finance, you should not divide by 100. Why you saw 3.33. Never likely came from your customer's CSV export when something went wrong due to the scraping. Implied volatility generally gets smaller as I get in the money and then grows. The values from option.iv are what is being saved into the CSV though. Oh, so if it's greater than 1, is it so small that they multiply it? Huh. What the heck? That's what I'm doing, I thought. I know what this is going. So now put the Black-Scholes is correct in principle, but only. 5%. So the at the money. So the Microsoft 515 call for today has we have around a 0.5859, like a 58% IV. Which, yeah, it's about right. And then when you go above the strike to lower prices, it gets lower or higher. There's some that are like 70 over here. So like the 465 call has an IV of 76. I have 72 here. So it kind of just depends broker to broker a little bit. Right? Interesting. So the outlier strikes are scaled while at the money strikes not. So it looks like it like flips. It'd be 100%, 100%. 100. Like here kind of flips. Well, I don't even really care about all these strikes out here. I only really care about kind of the first like 10 plus or minus the 5 at the money, basically. All right, we'll work on that tomorrow. A limit. Probably should just limit to plus minus 5 strikes, 10 strikes at the money. Okay. Cool. Okay. Cool. All right, you guys. I'll see you guys tomorrow. Thanks so much for being here and hanging out with me tonight. This was a really cool stream where we worked on our project. Got some more work done here, where we were actually starting to develop these Black-Scholes models and compare them against pricing. So we're going to plot these on a graph and see what strike prices within a certain limit would be the most enticing options for us. So thank you guys so much for joining me today. I'll see you guys tomorrow. Tomorrow we're probably going to continue back on to our MIT 6.0002 course, we need to complete the problem set or assignment 1 before we move on to lecture number 4. So because that is where the calendar lines up. So the assignment 1 is due before lecture 4. So please join me tomorrow around 7 p.m. PST, where we'll be completing the MIT assignment or problem set 1 for the 6.0002 course, which is like Introduction to Computational Thinking and something else. Anyways, I'll see you guys tomorrow. Thanks so much for being here. Bye, guys. Have a great one. Please like and